Every time a large language model reads a prompt, it performs a mathematical operation called self-attention. It compares every single token to every other token in the sequence. But as that sequence grows, the math scales quadratically. Double the input length, and the required calculations quadruple, expanding outward until the computational weight shatters the system's capacity. To generate text one word at a time, the model has to remember its previous work. It stores the calculated key and value states for every past token in a highly accessed database known as the KV cache. This creates a physical hardware problem. The KV cache is too large to sit next to the processing cores, so it lives in high bandwidth memory. To generate a new word, gigabytes of this cache must be dragged through a limited data pipe to the compute cores. The cores are incredibly fast, but sit idle, dropping cycles, simply waiting for the memory bandwidth to deliver the next block of data. Modern LLM design is a continuous war against this specific bottleneck. It is fought across architectural design and hardware execution and context scaling. Optimizing inference is no longer an exercise in maximizing raw compute flops. It is strictly an exercise in rationing memory bandwidth. The standard configuration for this math is multi-head attention. An input sequence is projected into initial query, key, and value representations. Instead of massive blocks, the architecture splits them into independent heads, capturing distinct aspects of language simultaneously. But every generated token requires loading the complete key and value cache for all heads. As the sequence lengthens, this massive footprint visibly strains the memory pipeline. This strict, isolated independence provides the model with its highest theoretical reasoning capacity. It remains the standard for specialized scenarios where maximum reasoning quality is non-negotiable and where inference latency is a secondary concern. While multi-head attention maximizes expressivity, the resulting memory weight makes scaling up batch sizes financially unviable for high-volume, consumer-facing production. To solve the KV cache size problem, engineers developed an extreme architectural alternative, multi-query attention. Instead of independent key and value states for every query head, all queries share a single key and value head. The cache size drops to 3% of the baseline. Tracks free up instantly, allowing the system to process massive concurrent batch sizes. But collapsing the matrices incurs a penalty. Models experience a drop in reasoning quality, suffer stability issues, and require significant uptraining to recover performance. The industry required a compromise to balance these extremes. The result is grouped query attention. This topology divides query heads into discrete groups. Within each group, queries share exactly one key and value pair. The outcome is striking. It recovers 98% of baseline model quality while keeping the memory footprint at an efficient 25%. It has become the architectural standard for modern production, utilized directly in the Llama 2 and Llama 3 model families. Architectural compression forces a deliberate engineering choice. By sacrificing marginal theoretical accuracy, developers secure massive gains in practical serving capabilities. Changing the architecture alters the model's weights, but the bottleneck can also be attacked algorithmically. FlashAttention computes the exact same mathematical operations as standard attention, but optimizes how the physical GPU executes them. This photograph shows a modern GPU. Surrounding the processor is high bandwidth memory, massive but slow. On the chip sits SRAM, extremely fast but highly constrained in size. Standard attention fails by creating massive intermediate matrices exceeding SRAM capacity. The GPU constantly writes these partial calculations back and forth to slow high bandwidth memory. FlashAttention introduces tiling. It breaks massive matrices into small square blocks. By loading tiles individually, data fits entirely within the ultra-fast SRAM. The block is processed end-to-end, and only the final output is written back to the slower memory pool. During the backward passive training, it uses recomputation. Instead of storing massive intermediate states, it saves only the softmax normalization factors and recalculates the rest on demand. This represents a highly specific trade-off, spending cheap, fast compute cycles to eliminate highly expensive memory bandwidth operations. Memory complexity drops from quadratic to linear, enabling 2 to 4 times speedups across both training and inference. FlashAttention proves that designing algorithms in a vacuum leaves massive performance gains unrealized. Software must account for physical hardware realities. As inputs scale to 1 million tokens, even optimal hardware hits a wall. At these extremes, exact attention math must be abandoned for subquadratic methods. Sparse attention achieves this by limiting the computation to specific subsets of tokens, utilizing fixed sliding windows or dilated structural patterns. It approximates full attention by explicitly ignoring irrelevant tokens based on distance or predetermined rules, processing only immediate neighbors. Linear attention takes a different approach, replacing the softmax kernel entirely. It compresses the context into a fixed size state, acting like a traditional recurrent network. When contexts stretch to millions of tokens, models must abandon perfect global recall in favor of bounded, localized approximations. State-of-the-art deployments do not choose just one of these techniques. They combine them into a unified production stack. A model like Llama 3 operates on multiple layers of optimization simultaneously. It utilizes grouped query attention at the software architecture layer, while executing the matrix math via FlashAttention directly on the GPU hardware. But optimizing the execution speed exposes a deeper limitation in context retrieval, documented in recent literature as the lost-in-the-middle phenomenon. Transformers form a U-shaped performance curve. Early tokens create the primacy tail, gaming immense combinatorial compounding. Final tokens form the recency anchor, teleporting gradients via residual connections. Middle tokens fall into the factorial dead zone, suffering severe fractional dilution and creating a structural blind spot. This U-shape is not an artifact of training. It is an exact geometric property present at the moment of initialization, completely independent of how efficiently the attention math is executed. Efficient attention mechanisms like grouped query and flash attention have successfully solved the hardware limits of sequence scaling. Overcoming the topological limits of context retrieval is the next fundamental frontier for machine learning.